we're going to look at how to predict the direction of a reaction. And if we say that a reaction is shifted to the right, we mean that we're favoring the products, in this case carbon dioxide and hydrogen. If we say that a reaction is shifted to the left, we're saying that we favor the reactants, which are carbon monoxide and water. Now if you look at the reaction quotient, you'll notice that it's the products divided by the reactants. So if you want to make a bigger number, you want to favor the products. And if you want to make a smaller number, you favor the reactants. So if you want your reaction quotient to increase, you'll want the reaction to shift to the right. And if you want the reaction to decrease, you want the reaction to shift to the left. So let's look at how we use that. Let's say we have the following concentrations, and then we will tell which direction the reaction will proceed. Now, if you write out the reaction quotient, which would be carbon monoxide or carbon dioxide times hydrogen, the concentration of those, divided by carbon monoxide and water, the concentration of those two, that would be the reaction quotient. And if you plug the numbers in, for this first set of concentrations, you get 0.0388, which is significantly less than the reaction equilibrium constant. So that means you're going to want the reaction quotient to increase toward the equilibrium constant. And remember I said if you want it to increase, you want to favor the products, so you want to shift to the right. So when the reaction quotient is less than the equilibrium constant, then the reaction will shift to the right. These next set, if you do the calculation, you get an answer of 1406. If you don't get that answer, make sure you bring it up in class and I'll show you how to do that. Now in this case, you want the reaction quotient to decrease toward the equilibrium constant. And if you want to do that, you have to favor the reactants, so the reaction has to shift to the left. So when the reaction quotient is significantly greater than the equilibrium constant, the reaction will shift to the left to favor the reactants. The third example is these concentrations. If you put that in the equation, you get a reaction quotient of 0.485, which is modestly less than the equilibrium constant. So this reaction will shift to the right, but not very much. So the reaction in the bottom concentrations, the third set, will shift to the right as well, and but it will not shift to the right as dramatically as the first set. Now, there's actually two types of equilibrium. There's what's called a homogeneous equilibrium, in which all of the substances, reactants, and products are in the same phase. That is to say, they're all in solution, they're all as a gas, etc. On the other hand, if a system is set up where the reactants and products could be in more than one phase, which is examples shown here with calcium carbonate and calcium oxide being a solid and carbon dioxide being a gas, then you have more than one phase, and that's called a heterogeneous equilibrium. And in a few slides, we'll show the effect of that. Now, if you have all gases, there can be a relationship of pressures between as an equilibrium as well as concentrations. And this shows what's called a pressure equilibrium constant. This is for a homogeneous equilibrium of gases. And you see that it looks very much like the concentrations, except it's using partial pressures for each gas instead of the concentration of each gas. Now, if you plug this into the gas law equation, there can be a relationship set up between the equilibrium constant using pressures and the equilibrium constant using concentrations. And this bottom line here is the relationship between those two. And you can see that they're related to each other by RT raised to the change in moles power. and delta N is equal to the product's coefficients minus the reactant's coefficients. So let's look at a couple problems where we have to write that out. So here we want to write the relationship between Kc and Kp for each of these reactions. So if we write this first one, Kc for this first one is going to be equal to the concentration of hydrogen times the concentration of ethine divided by the concentration of ethane. Now Kp is equal to Kc times RT raised to the n power. So Kp is going to equal this same number, which I'm not going to write again, times RT raised to the delta n power. Remember, delta n is going to be 1 plus 1 minus 1 plus 0, so it's going to be raised to the first power. So it's going to be equal to these concentrations times RT raised to the first power. RT raised to the first power is just RT. And obviously T is very important here and has to be in Kelvin. So what about this second one? Well, the second one, Kp, would be equal to the concentration of CO2 times the concentration of H2 divided by the concentration of water times the concentration of carbon monoxide times RT raised to the delta N. Well, it's 2 minus 2, or the 0 power. And that raised to the 0 power is 1, so that's going to be the same as Kc. This last one, Kp, is going to equal the ammonia concentration squared divided by the nitrogen concentration times the hydrogen concentration cubed times RT raised to the delta N. Well, delta N here is going to be 2 minus 4, or to the minus 2 power. It's 1 over RT squared. Moving on, I said that there was a different way of doing equilibrium constants if you were in a heterogeneous equilibrium, and this shows you the effect. What happens is you cannot express a concentration for a solid or a liquid, and so those are considered 1. So the concentration of calcium carbonate is 1 in this, and the concentration of calcium oxide is 1. So here in the second line, if you look at this, you see that the equilibrium constant is the concentration of carbon dioxide 1 over the concentration of carbon dioxide. For lead chloride, forming lead and chloride ions, it's going to be the lead ion times the concentration of chloride ion squared divided by 1, or just that product. Carbon plus sulfur gas forms calcium or carbon sulfide. In this case, again, you don't consider the carbon. You have carbon sulfide divided by sulfur squared. So when you have a heterogeneous equilibrium, if it's a solid or a liquid, not aqueous, but a liquid, like water, say, then it is not considered as part of the equilibrium constant. Now, if the water is a gas, it is. Moving on to a concept known as Le Chatelier's principle. This is very important, and you need to spend a little time thinking about this to make sure you understand how this works. Le Chatelier, if you notice, the position of an equilibrium is the concentration of the products and the reactants. So at any point in time, the concentration of the products and the reactants is called the position of the equilibrium. If you stress that, it means you cause some change to the position of the equilibrium. Either you change the products, you change the reactants, you change the temperature, you change the pressure. There are various things you can do to make a change. Le Chatelier's principle states that when a chemical equilibrium is put under stress, it returns to the equilibrium by counteracting the stress. And the stresses include changes of concentration of reactants, changes of concentration of products, changes in temperature, changes in pressure, or addition of catalysts. So let's see the effect, and I'll just walk you through this. Let's see the effect on various equilibriums. Let's say we have this equilibrium, and 1, 2, 3, and 4 represent 4 stresses. You start out with this equilibrium and you add ethene, which is one of the products. Well, if you add something to the right side of the equation, in order to alleviate that stress, it's going to shift the reaction to the left to get rid of some of that. Secondly, if you remove hydrogen, again, it's going to shift it to try to replenish that hydrogen, so it's going to shift it to the right to replenish hydrogen. Now this next one's a little tricky. In order to look at the effect of pressure, an increase in pressure favors the side of the reaction that has less molecules. Less molecules. So in this case, the reactants have 1 molecule and the products have 2 molecules, so when you increase the pressure, it's going to shift it to the left. If you look at the effect of temperature, it depends on which side of the equation the heat is on, if there is any heat. If there's heat in the reaction, then it should be considered one of the products or one of the reactants. In this case, increasing the temperature increases the heat. It's just the same as adding hydrogen or adding ethene, so it shifts the reaction to the left. Now stop the tape and see if you can figure out each of these before I tell you the answer. Okay, here are the answers. The first one is that you add carbon monoxide. If you add carbon monoxide, which is a reactant, it's going to shift to the right to get rid of that added carbon monoxide. If you add hydrogen, it's going to shift to the left to get rid of the added hydrogen. If you increase the pressure, you have 2 molecules on the right, 2 molecules on the left. Increasing the pressure doesn't do anything. And then if you decrease the temperature, decreasing the temperature is equivalent to removing heat. If you remove heat, it will shift to the left to try to replenish the heat that's on the left. You try it first and then I'll go through the answers. Okay, removing nitrogen is going to shift it to the left. Increasing the pressure, you have 4 molecules on the right or on the left and 2 molecules on the right, so it's going to shift to the right. Increasing the temperature will shift it to the left. Adding hydrogen will shift it to the right.